course on complex analysis. In this lecture, we are going to talk about the concept of upper bounds for moduli of contour integrals. Let us directly get into the lecture. If you see, first we have the Ml inequality lemma. Okay, we are going to prove something called Ml inequality, for which we need this lemma as a base lemma. Here, w of t is given to be some piecewise continuous complex valued function, which means what? Uh, this w of t may be written as u of t plus iota times of v of t, with t taking the values in this interval a to b. This may be written this way, or t is taking values in this interval. We may write it this way. Now we'll have to prove absolute of the integral is smaller than that of the integral of the absolute value of the given complex valued functions. So this is what we'll have to prove. Okay, let us get into the proof. So for proving this, first let me assume uh, when the value on the left is 0, that is, suppose uh, integral a to b w of t dt is 0, then this tells us that integral a to b w of t dt, this quantity has to be 0. This tells that the function w of t has to be 0. Okay, so if this is so, then of course integral a to b absolute of w of t dt is also 0. So if we mark this as equation 1, okay, we cannot say it as an equation. In equation 1, uh, in equation 1 is true when the function w of t is 0. Now assume w of t is not equal to 0. Okay, so now let us write integral a to b w of t dt. Okay, this quantity, this is going to be some non-zero complex number, because since this is not equal to 0, this is okay. We have only assumed this w of t is non-zero, but we do not have any assurance that this quantity is non-zero, but still it is some complex number. Okay, so if it is a complex number, this may be given some this is some complex number, right? So let me give some notation. Okay, mm, here we have not. Okay, no issues. Let me give any notation, right? Where alpha is a complex number. So when we integrate this quantity, we are getting some complex number. That is the ideology that I was trying to convey here. So with which put alpha equals r naught e to the power iota theta naught. Okay, then we would have integral a to b w of t dt is r naught e to the power iota times of theta naught. Okay, so from which if you write what is r naught, it is e to the power minus iota times of theta naught integral a to b w of t dt. Since r naught is a real value, uh, what? Since this is a real value, the corresponding value e to the power minus iota times of theta naught integral a to b w of t dt is also real. So we know that a complex value z is real if and only if real part of z is same as that of z. Hence, e to the power minus iota times of theta naught integral a to b w of t dt is same as that of real part of this quantity w of t dt. So let me take first of all let me take this quantity inside. Since it is independent of t, we can take it inside, and this does not affect the value of integration. So we have taken it inside, and using the properties of integrals, we may write this as real part of e to the power minus iota times of theta naught w of t dt. Okay, whether we are integrating and taking the real part, or we just take the real part and integrate, we are going to get the same value. That is what we have said. We again note that, or by observation, okay, we shall simply we know that real part of c is smaller than or equals absolute of c. Okay, so this is true for any complex number. Hence, what we get is real part of e to the power minus iota times of theta naught w of t is smaller than or equals this quantity. Okay, by the properties of absolute of complex functions, this is what we are going to get. So this absolute value is 1 for any value of theta naught. So finally what we get is real part of e to the power minus iota theta naught w of t is smaller than or equals absolute of w of t. Okay, so just a minute. Yeah, hence what e to the power minus iota theta naught integral a to b w of t dt. Okay, so this quantity is less than or equals integral a to b absolute of w of t dt. Okay, this is what we have proved, right? Okay, so what is this? This is equal to your r naught. And what was r naught? R naught was simply the integral. Okay, so we have come till this. Let us mark this as equation 2. Now, okay, this quantity is equal to r naught, right? Hence, r naught is this quantity and this quantity is this quantity. Consider integral a to b w of t dt, which is what r naught e to the power iota times of theta naught. So from which what I get is integral a to b w of t dt is absolute of r naught e to the power iota times of theta naught. And this r naught is what? So when you take the absolute of this thing, you are going to have simply absolute of r naught. So even if you take absolute, nothing is going to get changed, right? So without loss of generality, we may have this to be simply r naught, and this is smaller than or equals to, okay, this is smaller than or equals to integral a to b absolute of w naught d naught. Finally what we get is integral a to b absolute of integral a to b w of t dt is less than or equals integral a to b absolute of w of t dt, and this completes the proof of the lemma. Next, we are going to prove the Ml inequality theorem. Okay, here we have a contour whose length is L. Okay, suppose we are given some piecewise continuous function on this contour, and this M is some non-negative. Okay, I'll just have to change the color for better understanding. Yeah, so it is given the length of the contour is L. Suppose this function is piecewise continuous on the given contour, and M is some non-negative constant, which means M can be either positive or 0. So this is what they have said, such that this is satisfying this condition for all the points on the contour. Okay, now we'll have to prove this inequality. So this is known as Ml inequality. In order to prove this, first of all, we'll have to prove the lemma that we have proved just now. Okay, so let us start the proof. Let z of t with a smaller than or equals t smaller than or equals b be a parametric representation of the curve C. Okay, by the above lemma, we can have absolute of integral over C f of z dz, which is okay. First of all, this may be written as integral a to b f of z of t z prime of t dt, which is smaller than or equals integral a to b absolute of f of z of t multiplied with z prime of t dt, and this may be written as integral a to b absolute of f of z of t multiplied with absolute of z prime of t dt. These are written just using the definitions and properties of absolute functions. Okay, so as of now, just mark this as equation 1, and we'll have to plug in two results. Okay, so one is from the given thing, right? Since this is given, we are going to make use of this one. Okay, what do we mean by length of a contour? Uh, this shall be written as integral a to b z prime of t dt. In mathematical thing, the derivative of a arc, when you integrate the derivative of the arc over the given interval, you are going to get the length of a contour. And exactly the same, these ideologies we'll have to plug in now. So till now what we have got is absolute of integral over c f of c dz is smaller than or equals integral a to b absolute of f of z of t multiplied with z prime of t dt. So this quantity is smaller than this quantity alone, okay, is smaller than or equals m. Okay, this is by hypothesis that is given in the statement itself. Okay, so using that, this is smaller than or equals integral a to b m times of absolute of z prime of t dt. Since m is a constant, we take it outside, so m multiplied with integral a to b z prime of t dt. Okay, now we make use of the definition of length. So that is the mathematical definition of length of a contour. What we get is m times of L. So finally, integral over C f of z dz is smaller than or equals ml, and this is what we intended to prove. Okay, now let me make some remarks, okay, remark kind of a thing. Here the contour C and the function P and the function F, okay, both are given to be piecewise continuous, and hence the number m uh, is existing always. Okay, the existence, what I'm trying to say here is the existence of m is assured always as C and F are piecewise continuous in the respective domain. The domain in which we are considering these things is spoken here, right? So this domain is basically what? This is the interval, this thing, right? So these sort of a domain that we consider. So in this, the existence is always there. Okay. Now we'll enter into some problems. Okay. Here we are given an arc which is absolute of z equals 2. Okay, good. That lies in the first quadrant. So basically, what is this curve? This curve is a circle of radius 2. Okay, this is the curve. Here we are asked to consider only the part of the curve that lies in the first quadrant. So only this part is 2 and this is 2i. Okay, only this part of the curve we are going to consider. So this is RC. Now we will have to show that this happens using ML inequality. Okay, here the properties that we are about to use, just a minute. Okay, uh, properties to be used. First one, absolute of z1 plus z2 is smaller than or equals absolute of z1 plus absolute of z2. And the second one is absolute of z1, be it plus or minus, is bigger than or equals absolute of absolute z1 minus absolute of z2. And the third one is Ml Inequality Theorem. Okay, so these are the things that we will make use in this problem to complete this one. Okay, first let us consider integral over c absolute of z plus 4, sorry, z plus 4 upon z cube minus 1 dz. So by the lemma, we shall write this as integral over c absolute of z plus 4 upon z cube minus 1 dz. Right? Let us mark this as equation 1. Let us mark this as equation 1. And now consider absolute of z plus 4 upon absolute of z cube minus 1. So this is same as that of absolute of z plus 4 upon absolute of z cube minus 1 by the properties okay, by the properties what we have is absolute of c plus 4 is smaller than or equals absolute of c plus absolute of 4. This is nothing but absolute of c plus 4. Okay, and the other one is z cube minus 1. Either we may write this as absolute of z cube plus 1. This is one way, and z cube minus 1 may be written as bigger than or equals absolute of z cube minus 1, sorry, absolute of 1 with whole absolute. Okay, the same goes for the first one as well, but we will have to decide which is to be chosen and why. Here I'll choose the first one and I remove the second one, just because I have this z cube minus 1 term in the denominator. Okay, when I use the inequality involving bigger than or equal sign, when I take the reciprocal, that becomes the inequality with smaller than or equal sign. Okay, so this will imply that 1 upon absolute of z cube minus 1 is smaller than or equals 1 upon absolute of absolute z cube minus 1. Okay, that is why I am considering this inequality. Okay, so with all these, what we get is absolute of c plus 4 upon z cube minus 1 is smaller than or equals absolute of c plus 4 upon absolute of absolute z cube minus 1. Okay, now let us revisit the problem. We are given a circle absolute of z equals 2. So which means on the contour absolute of z takes the value 2, right? So this shall be written as 2 plus 4 upon absolute of 2 cube minus 1, which is 6 upon 7. Okay, due to absolute of c equals 2. This is the given thing. Hence integral over c f of z dz is smaller than or equals integral over c, and this quantity has become 6 to 7 dc. Okay, now we'll have to do the parameterization. Sorry, I have done something wrong, right? Yeah, okay, I shall have it as dc. Since this is constant, I take it outside. Absolute of c dz. Now I'll have to do the parameterization and do this thing. Else, okay, here I am going to give you an ideology, that is absolute of c dz may be written as, okay, in general setup I am writing it is z prime of t dt over the given limit a to b if t is defined in this limit, and that is what the contour represents. This is nothing but the length of a curve, length of a contour c. So which means we will have to now multiply the length of a contour with this 6 upon 7. So 6 upon 7 length of a contour. Okay. If you have to do it mathematically, yes, of course you can do it. So from the diagram, what we observe is that what is the length of the curve? If it is a complete curve, the perimeter is going to be the length of the curve. If you are able to find out the perimeter value and if you divide that by 4, you will get the value of c. So from the figure, the length of a curve is 1 upon 4 times of 2 pi r. So that is 1 upon 4 times of 2 into pi into 2, that happens to be simply pi. So with which what we write as integral absolute of integrals over c f of z dz is smaller than or equals 6 upon 7 times of pi, which is nothing but 6 pi upon 7, and this is what we are asked to prove. Okay. Next we have an integral. Here we are asked to show that this integral limit goes to this integral value goes to 0 as r becomes large. Okay, so this is what we'll have to prove. First of all, let us pay attention and try to identify what is given. Okay, here the function f of z is z to the power half upon z squared plus 1. So we'll have to make use of the properties that we have already specified in the previous problem. Okay, and this involves z to the power half, for which we take a branch, that is z to the power half equals exponential of half times of log z. We take this one and we shall give notation as what. Okay, before giving this a notation, let me do those things. Let z equals r e to the power iota times of theta. Then z to the power half will be r to the power half, or we may write it as under root r e to the power I theta upon 2. Okay, here your r is a positive value and your theta lie from minus half to minus pi by 2 to 3 pi by 2. Okay, only the positive side we have taken. So we have calculated all these things. Now let us calculate actually okay, this is how we do the parameterization. Okay, so after making the parameterization, let us see what is given and what are we going to do. Okay, it is given that z equals r e to the power iota times of theta. Hence absolute of z to the power half would be under root r e to the power iota theta upon 2. Okay, now let us see for absolute of z equals r, which is bigger than 1. Let us consider this way. Absolute of z to the power half, actually this becomes under root r. Okay, so this is equal to under root r, and absolute of z squared plus 1 is bigger than or equals absolute of z squared minus 1 whole absolute. So this is r squared minus 1. Hence absolute of f of z, this is what absolute of z to the power half upon z squared plus 1. This is smaller than or equals, this is under root r upon r squared minus 1. Okay, hence integral over cr z to the power half upon z squared plus 1 dz, absolute of this quantity is smaller than or equals mrl, where this mr is nothing but under root r upon r squared minus 1. Okay, so now what we are going to do is that we just do the simplification, but before that we'll have to find out the value of L as well. What is here? Let us revisit it. It is the semicircular path r e to the power iota theta upon 2. So from this we notice that the radius of the semicircle is r, and we are looking for the length of a semicircle, which means it is simply pi r. Okay, so from observation we get L equals pi r. Hence, integral over CR absolute of this value. Just a minute. This under root r upon r squared minus 1 multiplied with pi r. So this has now becomes pi r under root r upon r squared minus 1. So if you have to do further simplification, you may have it as like, from the denominator I take r squared outside, so it becomes 1 minus 1 upon r squared, and in the numerator also let me take r squared outside, so it becomes what? Simply 1 upon under root r. Okay, so r square and r square get cancelled, so we have pi upon under root r upon 1 minus 1 upon r squared. Okay, if we let r approaches infinity, then absolute of integral over cr z to the power half upon z squared plus 1 dz is smaller than or equals what? So as r approaches infinity, your numerator part goes to 0 and the denominator part goes to 1. So this is smaller than or equals 0. This forces that integral over cr z to the power half upon z squared plus 1, this quantity is 0. Okay, when as r approaches infinity. Okay, the next problem that we are going to see is given that without evaluating the integral, we are asked to show this. Okay, now here we'll have to pay attention to understand what is the semicircular path that is given to us. Okay, it is clearly said that we have a semicircular path from 2 to 2i. Okay, so I don't know whether this becomes a semicircle or not. So if this is 2 and if this is 2i, it is only a quadricycle, right? Okay, let us see whether it is completely a semicircle or simply only a quadricycle. Let us see this, right? So this is given, this is our contour C. Now let us evaluate absolute of z squared plus 1. So as we did in the previous problem, this is absolute of z squared minus absolute of 1 with whole absolute. So this may be written as absolute of absolute z squared minus 1, and this is absolute of 4 minus 1, which happens to be 3. Hence, we write 1 upon absolute of z squared plus 1 is smaller than or equals 1 upon 3. Okay. Now, if we know what is the length of this curve, we are done. We are done with this problem, right? So, what can be the length? If that is, we'll have to calculate the length of a quadricycle. So it is going to be, we know that perimeter is going to be what? 2 pi r. Here we are taking only the quadricycle. So length of C is nothing but 4 times of 2 pi, and r is what? R is 2 here. Okay, since absolute of z is given to be 2 and r, this 2 is the radius here, we get this to be pi. Hence, by ml inequality, we get absolute of integral over c dz upon z squared plus 1 is smaller than or equal to m value is 1 upon 3 and l value is pi. So it is pi upon 3. So we have completed the problem. The next problem that we are going to see here, it tells that CR is the upper half of the circle. So we don't know what is the circle with what radius we are going to take, but we are just going to consider upper half of the circle. Okay, we in the counterclockwise direction they have specified that. So this is the direction. Let us take this radius of the semicircle to be r. Okay, now we'll have to show that this happens. And after showing that this happens, we'll have to divide the numerator and denominator by r power 4, and then we'll have to show this goes to 0 as r goes to infinity. Right? So here the function given f of z is what? 2z squared minus 1 upon z power 4 plus 5z squared plus 4. Okay, and this is the circle that we have considered. Now let us consider this quantity, that is we are trying to evaluate the value of m. So this is absolute of 2z squared minus 1 upon absolute of z power 4 plus 5z squared plus 4. Okay, if you notice, okay, let us mark this as equation 1, and absolute of 2z squared plus 1 may be written as absolute of 2z squared plus absolute of 1. This is 2 times of absolute z squared plus simply 1, and this value is what? 2r squared plus 1. Now let us estimate this quantity, that is z to the power 4 plus 5z squared plus 4, which is the same thing. Now treat this as a single quantity. Okay, and this as a single quantity, or you may have this as one quantity and this as the other quantity. So we write this as bigger than or equals absolute of absolute z power 4 minus 5z squared plus 4 under the absolute sign. Right, now again writing this quantity may be written as absolute of 5z squared minus absolute of 4. We may substitute this in the place of this. So this becomes bigger than or equals absolute of, okay, z to the power 4. Actually, we have this minus sign here. So what shall we do? Okay, we can. We'll do the other way. Okay, not this way. Since we have the minus sign, it may be a little confusing for us, especially to me. So let us consider this way: z to the power 4 plus 5z squared minus 4. Now consider only this part, right? So we are just going to consider only this part, and this is absolute of absolute z to the power 4 minus 5 times of absolute z squared. So this is again bigger than or equals absolute of absolute c to the power 4 and minus 5 times of absolute of c squared minus 4. Okay, now we shall substitute the limits. So it is going to be simply r squared minus 5r, sorry, r to the power 4 minus 5r squared minus 4. Hope I am right. Okay, so hence by 1 we get absolute of 2z squared minus 1 upon z to the power 4 plus 5z squared plus 4 may be written as 2r squared plus 1 upon r to the power 4 minus 5r squared minus 4. And this quantity they have split into two terms. Okay, that is r squared minus 1 multiplied with r squared minus 4. We get these values. So if we find what is the value of L, that is length of C. Since we are given with semicircle, it is 1 upon 2 times of 2 pi r. So it is simply pi r, with which we conclude absolute of integral over c 2z squared minus 1 upon z to the power 4 plus 5z squared plus 4 dz is smaller than or equals pi r times of 2r squared plus 1 upon r squared minus 1 multiplied with r squared minus 4. And I suppose this is what we wanted to prove, right? So we have proved the requirement. Next, we'll have to divide this quantity by r to the power 4, which means what we are going to do is that pi r 2r squared plus 1, this quantity divided by r to the power 4, r squared minus 1 r squared minus 4 divided by r to the power 4. So if you take okay, so let me do this in the next page. So this one by r we have inside what we had 2r squared plus 1. So we take r squared outside, so this becomes 2 plus 1 upon r squared, right? So this quantity divided by r to the power 4. So this is what we have, everything divided by we take r squared from this first quantity and from the second quantity. So this becomes 1 minus, okay, if you notice here it is r squared minus 1 and r squared minus 4. So 1 minus 1 upon r squared multiplied with 1 minus 1 upon, 4 upon r squared, everything divided by r to the power 4. So here these two gets cancelled, here we this thing gets cancelled. So what we have is pi uh, okay, let me write it as pi multiplied with 2 plus 1 upon r squared. Okay, we may have this also to be pi upon r divided by 1 minus 1 upon r squared multiplied with 1 minus 4 upon r squared. Okay, and where does it go to? Okay, that is as r goes to, that is what we are saying is that as r approaches infinity, then integral over c, whatsoever the function is, you just write that function d is at smaller than or equals limit r approaches infinity pi upon r 2 plus 1 upon r squared divided by 1 minus 1 upon r squared and 1 minus 4 upon r squared. Using the algebra of limits, one may notice that this quantity alone goes to 0 as r approaches infinity. Similarly, this goes to 0 and this goes to 0 and this also goes to 0. Now, seeing the results together, so this quantity goes to 2 plus 0, which is 2. Similarly, this goes to 1 and this also goes to 1. So as r approaches infinity, what we are going to get is 0 multiplied with 2 divided by 1 multiplied with 1, which is 0. So this is what we were asked to prove and we have very well proved it, right? Thank you.